So as I said, today I will solve some problems in R, specifically some empirical exercises in R. That will be very helpful, I think, for you guys, because that significantly reduces time to solve problems. I mean, the R Studio R significantly reduces time to solve problems. So again, so please go to our course, go to course documents, then scroll down, go to week 12 folder, and then you will see 11/11/2020 class materials and download all of those. Okay, please let me know when you are ready so that I can start. So it will be.
Wait, download everything?
Download everything, yes, absolutely everything. So it will be very beneficial to you guys if you do this with me, right? Because in that case, you'll learn more. But also, you have access to all of these. So these are some Excel files, some PDFs that have some good information. Those are from the from internet, but I think that's very helpful. And also there are some Excel files that contain data that we will use today. So again, for everybody to repeat. So please go to class. So first, log into your go to our course. Go to course documents. Scroll down. Then you will see week 12 folder. Go there, and then you will see 11/11/2020 class materials. And I said, please download all of those. You will see my screen, right?
Yes, sir.
Perfect. So then download all of them, and I will start in a few minutes. Okay, maybe I can already start because it's already 2:36. If you guys have already downloaded all of these, so then please open your R Studio. I will open my R Studio, and I'm not sure if you see, probably not. So let me share this screen. So these are some simple codes I wrote yesterday, and that will be useful for us today. I will now, so this is, let me run this to clear everything. I will close this and I will start from the beginning, right? So did you guys open R Studio?
Yes.
Okay, great. So please be involved in class so that we move smoothly and not too slowly. So then go to File, Open File, and then locate the R script on your laptops. So I have it in Downloads, and there I will see SC 11/11 class R. That's the R script I made today. And click Open, and that will open this R script. Okay. So now let me open the problem. If you guys have any questions, please stop me at any time. Empirical chapter 5. this. Okay. I think that's it. Okay, so this is the problem I will do today. So you have already downloaded this Excel and this description that is already on your computers because I already asked you guys to download certain stuff from Blackboard, and that stuff includes this. Guys, are you with me? So please let me know that I'm not talking to myself.
We're with you.
Yeah, we follow.
Great. So we will answer to these questions, right? But first, we have to run a regression of average early earnings, AHE, to on age, right? First of all, guys, so whenever do any data analytics, right, you have to know the variables. You have to understand the data well. Otherwise, it doesn't really make any sense to proceed, right? So you have to understand the data. You have to understand every variable that you have. So everything is in this description. Right? So that's why we have this PDF file here. Now let me open the Excel. Not Excel. The Excel, the data in R. That's what I meant. Let us open data in R. Guys, at this time, you probably have opened your RStudio because I already said it. Then what I want you to do is the following. Clearly, this code will not be correct because this is the location of the Excel file. So what I want you to do instead is the following. So first of all, please run command lines 5 to 9. Okay, guys, are you with me? Please do it. And then run command line 11, right? It will take a few moments, but they will be pretty quick. Right, so that don't worry about it. It's installed. Maybe you have already installed these packages on your lab, on your computers in this hour, but if not, then this will take a few moments, but it's pretty.
Wait, I'm sorry. What file did you open?
The 1111 class. That's the R script, which is
Yeah.
named 1111 class.
Class.r. Yeah.
Yes.
Professor, how do you run the
You just select.
RM?
You select this. Do you see my blue script?
Yeah.
R. So you just select these lines 5 to 11, and then click run here. But I already did it, so it doesn't really. I'm doing it once again. So it's once you run it on your laptop in R, that's enough. Now, the next thing I want you guys to do is the following. First, we need to set our directory. I mean, the directory where we are working. Right? Do you guys see what I mean? So where all these Excel files, R script, other files are located, right? For that purpose, please go to session, guys, go to session, and then you need to follow, otherwise you may get lost. go to session, and then go to set working directory. And then please choose directory. Click on that. Are you guys with me?
Yes.
Yeah, we're following.
Click on choose directory, and then just locate your files. I have it in downloads. I just click on downloads, and then I click on open, and that's it. And now what?
Wait, what are we locating?
So you are locating
This file, the 1111 class R, or are we locating?
you are locating a folder where you saved the files I told you guys to download a few minutes ago. For that, go to session, go to set working directory, and then go to choose, and then choose directory.
Oh, my thing just crashed.
Well, you have to open that once again then. Choose directory, and then locate the folder where you saved the files I asked you to download from the Blackboard. Am I clear? So I have those files in downloads. So I do this, and then I just select downloads because I know the files I downloaded is here, and then I click open, and I'm all set. If you see here is the comment, right? That is telling us where our files are and that everything is fine because we don't have any errors. So I just copied this and paste it here. For the next time, you can also manually set your directory, but I think it's always better to do this the way I just told you. Go to session, set working directory, and then choose directory, and then choose your directory, and that's it. So guys, if you did all of that, the next step is to open. So while because we already set the directory, we now, that means that we are good to go, right? So because then we will be able to open Excel data that we have in Excel, which is in the directory that we selected right few seconds ago. So now we will open the Excel file. So to open Excel file, please go to File. Guys, I will be asking you, are you with me? Are you with me? But that is just to check that you are really following. So please don't get irritated. So go to File. Now what are we doing? Now we are just opening data in R, data that we have in Excel, in that Excel that is in the directory that we chose a few minutes ago. Okay, so then go to File, and then we need to find import. Where is it? So import data set. We know that our data set is in Excel format. Do you guys see what I mean? We know that, right? So because we downloaded it from Blackboard, and we saw the data is in Excel format, but there are other formats as well: text, SPSS, SAS, data. But those are irrelevant right now because we already know that that data that we have is input in Excel. So we'll just find import data set, go to File, import data set, and then we know that it's in Excel format, so that you choose from Excel. And then you click on that. Guys, are we good to go?
Yes.
Click on that. And then we just need to browse. Right? So do you see this? Browse. Click on that. And then locate the Excel file. I have it in downloads. Okay. And the name is CPS 08. selected. Guys, do you see my screen? Like, what do you see right now?
Yes. We see you in your download files, and on the right side, there is AHE,
Great.
year,
So that's
bachelor,
yes.
female, age.
Yes, that's
There's
exactly what I.
38.4615402.
It will be very time consuming if it continues that way. So, but that's great. So you see the right thing. So then click open, and that's it. So now we see everything is fine, and click on import. And this is your data set. I don't really need it. I will just close it. And here you see the command, right? I copied it. So this is copied here, but you know, you're already good to go. So now we can run our model. And remember, we are supposed to run a linear model, ordinary least squares model, where the dependent variable is AHE, average early earnings, and the independent variable is age. So this is just a bivariate model, but we have just the one independent variable. Okay, so that's the command for that. So up until now, are you guys following?
Yes.
So this command tells us, so you can call it whatever you want. I just named it as linear model because it's a linear model, but you could name it whatever you wanted. Right, so it's a linear model, and that's why I called it linear model. And then LM test, this is a function, right? This is a function which calculates everything related to the LS, right? Regression. So, and the function is written in this way. So the parentheses, and then you have AHE, that sign, age, comma, and data equals CPS 08, right? So this means that you are just regressing AHE on age, but using as your data, you are using CPS 08. And then you click and select comma 21, and then just click on run. So it means there's no error, nothing. So that means we did it right. There's nothing wrong with it. If there was anything wrong, then it would get error, right? So, and then you can just see certain outputs of your linear model. So select command line 23 and then click run. So what it gives us is just the coefficient estimates, right? It gives us the coefficient estimates. We have one independent variable, which means we have one slope coefficient. In this case, it's the estimated slope coefficient is 0.605, and we have also estimated intercept. But also, we know that there are lots of other things that we are interested in to know when we run the OLS regression. Can you guys tell me what are those other things that we are interested in to know when we run the linear regression model?
The beta points.
The estimated betas are here, right? What are other things? What are other estimates that we are interested in to know when we run a linear regression model? What are those other estimates that we want to know? Those are just the estimates of the slope and intercept. So let's say you want to test the hypothesis, right, about the betas, not beta heads. You test the hypothesis about the betas, right? So let's say you want to test the hypothesis about beta 1. What do you need to know for that?
The T-stat.
The correlation.
T-stat, true. But to calculate T-stat, what do you need to know?
Standard error.
Estimated standard error.
Beta 1 hat.
Beta 1 head is here. You guys are doing well. So beta 1
Standard.
exactly. So
Sigma beta 1 hat.
exactly. So this is not enough, right? So we need to summarize. So if you run this, if you run this command line 25 summary of your linear model, that gives out a lot of good stuff, right? So we have many parameters. So what do we have here? This is the beta 0 head. This is beta 0 head. This is beta 1 head. Okay, guys? This is estimated standard error, or in other words, estimated standard deviation of what? Guys,
Professor, can you go back? How did you get the
so it is here. So 25.
25?
If you run command line 25, you'll get this.
All right, thank you.
So my question is, what is this highlighted part, 1.18426?
The standard error. Estimated standard error for intercept. Beta 0.
Very good. I praise you because you said estimated, right? So it's because that means you understand it. So it's estimated standard error, or in other words, the estimated standard deviation of what?
Beta hat 0.
Great. You did not say beta 0. Perfect. So guys, it's the estimated standard error or estimated standard deviation of beta hat 0 is absolutely right. Whoever you are.
Extra credit.
Now, what is this t-value? What do you think that is?
The test statistic for intercept. Is it?
Exactly. True. And how is it obtained?
T over standard deviation. A standard error.
What do you mean by t over standard?
It's B1 minus 0. Well, depending on the hypothesis, divided by standard error.
Exactly. So the hypothesis here is that that beta 0 is different from 0. Sorry, beta 0 is equal to 0, and then the alternative is that beta 0 is different from 0. So in that case, how would you obtain this 0.914?
The intercept divided by the estimated standard error.
So can you tell me the numbers?
1.08228 minus 0, all in parentheses, divided by 1.18426.
And you would obtain this, right?
That is correct.
Perfect. So
You get extra
then,
credit.
guys, you don't really need extra because you do really well, right? So in the midterm, you did pretty well. So I don't think you need it. So now tell me how we obtained this p-value.
That's the p-value.
Exactly, that's the p-value.
You
right?
get the negative of the t-value, and you find out what is probability, and then you times it by 2.
So this is 2 times. Can you tell me this is 2 times probability that capital Z is less than minus 0.914, right?
Yeah.
Exactly. And the same thing for, what is this?
That is the beta 1 hat.
Yes, you should say hat. And that's the estimated beta 1. And that stands in front of H, right? In the model. That's why we have it, and we have all this. So also we have other measures. So here we see the degrees of freedom is 7709. So then can you tell me what is the number of observations?
7711.
Why?
Because the degrees of freedom is minus by 2 in this, right?
Why is it minus by n minus 2?
Isn't it? I don't know. The formula should be like n minus 2. Or like I don't know. I don't know.
Okay, but
It's n minus k minus 1.
yes, so what is k in our case?
It's minus 1. Never mind. I
Exactly.
remember one of the formulas have minus 2.
I will tell you then. So it is n minus k minus 1. K is number of slope parameters or number of independent variables, because number of slope parameters is exactly equal to the number of independent variables. So in this case, how many slopes do we have? Or how many independent variables do we have? Just one, right? So, okay,
One.
then it will be n minus 1, but then also have to subtract the 1 because that one is for the intercept, because we have only one intercept. Usually we have only one intercept. So it will be n minus 1 equals to 7709. And then from there, you recover the number of observations, right? Which is 7711. Then we have r squared, which is that you also have adjusted r squared, which is that you have f statistic, which you don't, I mean, maybe you know, but we have not yet explained that. We will explain that in the future. Okay, and this is the p-value of the Vol regression. This is the p-value for the f stat that we will explain later. Okay, so this is pretty good, right? So we have all this information, but can you tell me what problem do we have here?
Heteroskedasticity.
Exactly. So we have a problem which is known by heteroskedasticity. Can you tell me what does it mean?
We can repeat that.
Can you tell me what heteroskedasticity means?
The variation distribution is not consistent.
No. Think about it. Heteroskedasticity means that the disturbance does not have a constant variance.
Oh yeah, I meant disturbance, not the variance.
Okay, so what heteroskedasticity means is that the disturbance does not have a constant variance. Am I clear?
Yes.
Why is it a problem? Why is the heteroskedasticity a problem?
Because the data is calculated using homoskedasticity.
No, the heteroskedasticity is problem because if you have heteroskedasticity, then if you run a linear model and if you do not correct for heteroskedasticity in the disturbance, then you obtain wrong, invalid, wrong estimates of the standard deviations. So these two numbers, what did I do? So these two numbers would be wrong if we have heteroskedasticity in the disturbance term. Am I clear?
Yep.
Okay, that's a problem, because in that case you would not be able to obtain the correct t-value, because you said a few minutes ago that the value is obtained based on estimated standard deviations, right? P-value would not be correct as well. Then you would not be able to draw correct inference, meaning you would not be able to test the hypothesis about the true population parameters, right? Okay, so guys, good news. So bad news is that Excel does not have a built-in function that corrects for the heteroskedastic disturbance. Okay? Excel does not have a built-in function for that. So what you really need is that to obtain a heteroskedasticity corrected estimated standard deviations. Am I clear? We also call those heteroskedasticity robust estimated standard deviations, right? There are a few ways of correcting heteroskedasticity in the model, specifically in the disturbance. There are a few ways of doing that, and those ways are listed here. Right? HC stands for heteroskedasticity corrected. H stands for heteroskedasticity, C stands for corrected. Heteroskedasticity corrected 0, heteroskedasticity corrected 1, 2, 3, 4. Those are just ways of obtaining, different ways of obtaining heteroskedasticity robust or heteroskedasticity corrected estimated standard deviations, right? There might be slight differences in those obtained estimated standard. The thing is, those are different ways of obtaining correct estimated standard deviations, right? But the thing is, since these are like different ways of trying to solve the same problem, so they may have slight differences in the results. Do you see what I mean, guys? You can try all of those. I will just try this HC1. So coef test is a function that gives us heteroskedasticity corrected estimated standard deviations for the parameters, for the estimated parameters. So this is the name I gave to my model. VCOV stands for variance covariance matrix. And VCOV HC type equals HC2, HC3, H3, HC4. Those will give you guys very similar results. So let's do this. So please run command line 29, okay? And let me know when you are done.
Yep, I'm done.
I'm done.
So now what I want you guys to see is the following. So these are the results from before, right?
Yeah.
These are the results from now, right?
Yeah.
Do we expect, so let me cover this. Do we expect that the estimates will be different?
Yes.
No, I mean the estimates of the parameters.
No.
No, so, and then you see that, right? So you see that the estimates are exactly the same, okay? So guys, heteroskedasticity is a problem that affects the estimated standard deviations, not the coefficient estimates, right? What is it? What is a problem that affects the estimated coefficients? Can you tell me? What gives us different estimated coefficients?
The data, like the variance and the covariance.
Omitted variable bias, guys. I will talk about that later. If you see that the coefficient estimates are different, they are different simply because the model is suffering from the omitted variable bias, right? Now, do you see that the standard errors are different? Estimated standard errors.
Yep.
So see, okay, these are corrected. These are wrong. So now let's go back to the question. And it says the coefficient on age shows that the change in early earnings for every 1 year increase in age. That's pretty easy to understand that, right?
Yep.
Yeah, so now let's
There
go.
is black box on your screen.
Oh, sorry. How about now? This is an easy question, guys, right? So just you need to take a look at the variables, definitely understand what units of measurement they have. And this is pretty easy, right? Now, given the following hypothesis, is the coefficient on age significant or not? Do you reject age now? If you reject age now, that means what? The coefficient beta age, the slope coefficient, is not significant, right? So if you fail to reject age now, then beta age is not significant, right? In statistical sense. But if you reject age now, then that means that the beta age is significant, right? Let's do it. So at 5%, do you now see both of the screens?
We see
Yes.
the one.
You see only one?
I see the homework and the R studio.
Okay,
Yeah, R is in the background, homework is in front.
I want you guys to be seeing both. So, so when you look at the estimation results after you correct for the heteroskedastic disturbance, would you reject this hypothesis or not? At 5%.
No.
So you see this here, right? So this is 2e minus 16. That means it's a very, 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 very small number. It's very, very close to 0, guys.
Oh.
Like a minuscule number here. You have a very big test statistic, right? 15.0232.
I was looking at the 1.16, that's why.
Yes, no, they are asking not about intercept, but about age.
Yeah, sorry.
So you reject it, right? We reject age now. Okay, okay, we understand that, right? Then here is a problem. This is mistake. This should be 95%, okay? Guys. And
Yes, Professor.
okay, so now we want to build 95, not 99. This is the typo. We have some typos on Pearson. That's fine. I still give you homeworks. I still want you to learn. But if there is a typo, everybody will make a mistake. So you will not suffer from anything. So you will not, your grades will not suffer from that. But I'm telling you, this is a typo. Should be 95%. Okay. Am I clear? And now we want to build a 95% confidence interval for what? Um, Okay, where do I have it? Ah, okay, so this is for what? Just to know beta of H. Looks like I don't have it here, but we can do it, right? So you see my Art Studio, guys?
Yes, we do.
So let's calculate this confidence interval. There will be Z minus 1.96 times the estimated standard deviation, which is this. Okay. And then, oh, okay, that's fine.
I think they have it above already. Like
Do I have it about where?
line 40 to line 42.
42. No, this is a different numbers. These are different numbers. No, this is a different question. I don't have it here. It's strange because I did it yesterday. So, but you see this number, right? 0.5260.
Yeah.
This is 0.526, 527. It's pretty close to this, so you would be selecting this, right? And then this will be the lower limit. The upper limit will be this, but with plus, right? And you run it, and you see 0.6839. And you have 683 here. Okay. So the answer will be A. The confidence interval will be calculated as this, right? Guys. That will be the confidence interval at 5% significance level for beta 1. Okay. But also, I see I did it in this one command, guys. See, do you see this command? CI
Yeah.
for confidence interval. So I think I did it here in one command. This is like, you don't even have to write it. I just showed you, right? And that gives you this, right? This is exactly equal, not exactly, but this is equal to these numbers, right? Do you agree with me?
Yes. I did it. I got the same.
Yeah, so you know how to do this, right? Good. So now you are able to do this in R to find correct estimates and deviations, to find correct confidence intervals for beta 0, beta 1, whatever coefficients you are supposed to. Okay, sorry, the confidence interval for whatever coefficients and.
So, Professor.
Yeah.
So for any like I don't know like Excel file you give us, we can use R Studio to import the file into R and find all the values in R.
Yeah. So do you see that it's not difficult, right? So or am I? So it's not really difficult, guys. If you are following, and if you really understand all of these, pretty easy, right? And it's pretty quick. So in one command, we obtain these, right? So which is like the correct. What is that? These are like the correct confidence interval for age parameter. So, and this is what? Can you tell me what is this? Do you see the highlighted part?
Yes.
And that's the confidence that's the correct confidence interval for the intercept at 5%. Okay. If you want to get the correct confidence interval at 1%, then you would write here not 0.95, but sorry, 99. Okay. If you wanted confidence interval, let's say at 74%, then you would write 0.74. Level would be 0.74. Nobody does it because we all only are interested in the conventional levels of significance, right? Or confidence. But you get the idea, right?
Yep.
Okay. It's very good. So the next question. Given the following hypothesis, this is also, here is also a typo. No way you can get this, but it's okay. How would you test hypothesis that H0, which is H now, that beta of H equals 0.50? How would you test that hypothesis? First of all, you need to obtain correct use heteroskedasticity corrected.
Professor, you're muted, I think.
Guys, am I muted? I don't know.
You can hear you.
Not anymore. You're good.
So now I want you guys to tell me, how would you calculate T-stat for this hypothesis? Guys. It would be beta hat H minus 0.5 divided by what?
By sigma.
Sigma hat of beta hat H, right? Or which is where? Which is here, right? And I have done it on line 41, guys. Okay. And you run it, and you obtain 2.67152. And do you reject this H now at 5% significance level? Yes, because 260, 7152 is greater than 1.96, right? Which is the critical value at 5%. Okay, then the next question now. So this is incorrect, so don't disregard it. Now let me do this. Based on the regression, the expected average early earning wage for a person of 20 years old is what? You just plug 20 in the corrected heteroskedasticity corrected model. Or it doesn't really, you don't really have to do it because heteroskedasticity does not affect the coefficient estimates. So you just run a line number 43 and you obtain 13.18 182. Okay, so that's the answer, 13.18. Okay, so then we need to run the model for only females, okay? And that can be done using this command line, which will be different from you guys because I edit these two lines here, right? Please find this line in your RStudio, R script. So this tells us what? I called this model, it's a linear model, but it's for females, estimated for only females. It's a linear model, that's the function. And the dependent variable is AHE. Independent is again age, but data is not the full data, but it's instead a subset from CPS 08 data where comma stands where female equals 1. Means that we are running this model for the subset of data, and the subset only contains data on females. That's how you read this line 52. Guys, are you with me? Are you following?
Yes.
So then please locate this line in your R script and run it. And then we want summary, right? We want summary of this new model, which is linear model for females. Please locate that command line and run it. And we have these estimation results. And we want to understand what is the next question. The next question is, okay, then the question is, okay, we'll see that the right answer is the average based on the estimated result that the estimation results for the model from the model for only females. You will see that the average early earnings of a woman 30 years of age is 3.46 more than for a woman of age 20. So how do we know it? So we simply need to calculate that. So do you guys see line number 56?
Yes.
So that will be different in your script because I edit these two lines, right? But please, you should not have any difficulties to find this line.
3.46.
So you understand this, right? You understand everything here. Do you understand everything here in this line?
Yep.
How about others, guys?
I understand.
Yeah. So then you just run it, and you get this number, right? And then this is 3.4634, and this is exactly what where is it? So this is exactly what it tells. Then we have to do the same thing for males. That is also done here. And then the next question is, okay, you can do the same thing for males as well. So it is done here. I called the mod, okay, sorry. I called this regression a linear model for men. And you do this, but in this case, female is a dummy variable and it's 0, right? Because we want to run the model only for men in this case. I do the same thing, right? And summarize. And then you see what? That the expected average early earnings for a man 30 years of age is $20.38. How do you know this? You know this from this. The problem, do you guys see both of my R Studio and also the Pearson?
Yes.
Yeah.
How do we know this? Based on the estimation results, you have to check all of that. Am I clear? Right?
Yes.
But you know how to do it. Based on the separate regressions for men and women, we would conclude that, and then you see the estimate, the difference between the estimation results of the slope coefficients from the only males regression and only females regression, right? And you see the difference here is equal to 0.43. And that's why that's the answer. And then the next is a little bit challenging question, but it's not really difficult. Do you guys remember we learned how to test the hypothesis about the difference in means? About the difference in the two population means, right? We need to apply that reasoning to this question. This one. Okay, so what's the question? The question, so we are supposed to test whether the coefficient in age in the female regression model is different from the coefficient of age in the male regression model. Okay, so guys, please listen. So this is how I calculate the t-stat. So this here, guys, is exactly equal to this, right? And what is that? That's the estimated coefficient from the male only regression. Minus, that is what? The coefficient estimate of age from the female only regression. Can you tell me what is the hypothesis here? Can you help me? So what is age now? Beta, het, male, minus beta, het, sorry, female equals 5, right? Is that our age now?
Yes.
No, it should be 0.
Oh, yeah, I know.
You know, right? Yes, I'm sure you know, but the thing is why? Tell me. What is the hypothesis here? Do you see the highlighted part? I'm asking to everyone.
Are you back on
Yes.
our homework problem? Now, yes.
So it should be it should be 0, right? Why should I have it 5? It should be 0, right? Is there a difference? If there's no difference, then that's it. So then it means that you fail to reject H now. But if there's a difference, then you will reject H now. Guys, are you with me?
Yep.
So this is like implicitly, this is like minus 0, right? It's a difference minus 0. This 0 is the hypothesized value, guys. And then what do you need in the denominator? So what is it? So can you tell me what is it?
Is the estimated standard error
For
male plus the no.
that's the, so you started very well. So this whole thing that you see in the denominator, that is what? Estimated standard deviation of what? Of
Male and female.
of z. Okay. So and that's the square root from the variance. So what is this inside part? That's the variance of this, right? Estimated variance of this, right?
Yep.
Okay, so we have to so estimated variance of the difference in these two estimated coefficients will be the sum of the variance of each of the coefficients, which I have here. And since we assume there is no correlation between the two coefficient estimates, then we can simply disregard the covariance terms, and the variance of the difference in these estimated coefficients will be that, and you take a square root of it, and you get the estimated standard deviation of the difference in these two estimated coefficients that goes into denominator, and then just run it, select that, and run it. That's the test statistic. Do you reject H? No. Yes, because at 5%, the critical value is 1.96. It is quite smaller than 5.47, 6649. Do you see my RStudio, guys?
Yes.
So then means it will reject, we reject H now. The last question here is also, they say, challenging, but for you guys, this is a piece of cake. Using the results in part 9. Where is this part? I don't know. So do we reject this? We reject. I did it already, right? So we reject it. So that completes this
No
problem.
problem.
So we already completed this problem. So whatever you learned from today, you can apply that to a lot of problems that also are part of the homeworks, especially of the empirical homeworks. Why? Because you know how to run a model, linear model, how to obtain the correct heteroskedasticity robust estimated standard deviations of the coefficients. You know how to construct confidence intervals, how to test hypotheses. You know all of this, right? So simply after I mean, if you need, take a look at this class recording, work on this yourselves, on all of these yourselves. This is really something that is I think very useful, guys, in the future as well. All right.
Professor.
Yes.
So for like, so I say for like the second question of this imperial homework, I just download the Excel file that's attached to the question, and then I just open it in R, and then it should have all the formulas already for me, or like I can.
You will have to modify, right? So you will have to modify certain stuff, right? So for example, maybe you have a few regression. a few independent variables, right? So you will have to slightly modify to apply these codes to the problem in hand, but this should be like enough, right? Because after you clearly understand how this works, how we solved today this problem, then you will realize that you can apply that to many other problems that are similar. Now let me do another problem, which is this is 6.1, and I don't think I'll manage to do this, but I simply let me close it. I will continue next time. But you already have all these codes, guys. I've only left this, but look at this problem and then also take a look at this code. You'll find it pretty easy to do. But I just want you guys to open a new Excel file. Are you guys with me? So go to File, Import from Excel, and then browse another Excel file that was part of the files I asked you to download from Blackboard, and then you will see locate college distance Excel, and then open it. And then when you see this is here, import. The only thing I want to tell you, and then I will stop, is the following. So maybe you want to run a model which is bivariate, which means that there is only one dependent. We usually have only one dependent, but there are models where you have a few dependent, but okay, usually we have one dependent. And in this case, one independent, right? So which is in this case, dependent is education, independent is distance. So can then and you run a model and you get the estimates, right? When you summarize. Guys, do you see my RStudio?
Yep.
But maybe you want to run a model that has a lot of other independent variables. How do you modify? You just say distance is my first independent variable, then plus stands for like I want to have another independent variable, plus female is a dummy variable, which is 1 if a person is female and 0 if a person is male, plus black is a dummy variable, which means if a person is black, then we have 1. This variable takes value 1. If a person is not black, then it takes value 0. Hispanic by test, then so first I said already, guys, you need to understand the meanings of all these variables, right? So we also have the PDF file that clearly tells us what are these variables, what is this data set about, what are the units of measurement of these variables, and then so in this highlighted part we have how many independent variables. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 independent variables. And they are taken from data which is in the Excel file named college distance. And then you run this model and then you summarize. See what you see, what you get? We get this. So can you tell me what is this? Guys, that's the estimated slope coefficient for the variable Hispanic. That's the estimated standard deviation. That's the t-value, t-stat, and that's the p-value. This stars stands for significance. 3 star means that it's significant that there is 1%. 2 star is 0%. 3 star is 2 star is 1%. All of this. Take a look at it. But are those numbers correct, except this first column. They might be suffering from the
No.
yeah, from the heteroskedastic disturbance. So let's do this. Okay, where do I do this? Let me do this here. Curve test, linear model 3 is here, and then let's see, run. So then this number should be correct, and if you see, so the slope coefficient should not be affected much. They're pretty much the same, and you will see that the estimated standard errors will be different, and you will see this. There will be certain differences, right? So let me close today's class here. So guys, thank you very much for being here. I already uploaded all of this on the CUNY Blackboard. There's no class notes because I did not have any, did not write any. I just was working in R today. So take a look at this again. Work on this yourselves. This should be very helpful in the future. Okay, guys.
Thank you, Professor.
No problem. See you next Monday.
Thanks, Professor. Have a nice day.
You too, guys.
Thank you.
See you on Monday.
Thanks.